All
All
right.
right.
Well,
I think
welcome. Are
we're
you going to start
live.
us off, Doug?
We're good. Okay. Well, good evening, everyone. Welcome to the American Public University System's Wallace Boston Observatory. We're going to do some remote astronomical observing at our star party tonight. The observatory is located in Charlestown, West Virginia, and I am situated in Atlanta. And our chief astronomer, Dr. Kristen Miller, is in Houston, Texas. And we have um, many of our students, both undergraduate and graduate students, who are going to take us on a tour, a guided tour with a telescope to look at some celestial objects. I have to say that we are fighting a few clouds. We've done this 2 times before and we had the same scenario, but miraculously we were able to take a look at several objects. And the first time we did this 5 years ago, for the SESA conference, it did clear up. But welcome to the star party. We do have a backup if we get clouded out. And I wanted to just say a few things about the observatory before I hand it off to Dr. Miller and her students to begin the party where the fun begins. Our story was, and you see a picture of the exterior of the dome. It sits on top of the IT building up on the 5th floor, and we have a 32 ash dome that you can see, and the sky at this moment looks pretty much like that, partly cloudy. So we're hoping for our sky, and then you're taking a look at the big eye, as I like to call it, the 24-inch plane wave CDK telescope. This is a state-of-the-art research grade telescope, and it sits on a pier. If you're ever in Charlestown, and I happen to be up there, I go up there several times a year, I'd be happy to give you a tour of the observatory. It's pretty cool going inside of the observatory. But for our technical gurus, the telescope has a plane wave A200 mount, a very precise mount that guides the stars, guides on the stars as the Earth rotates on its axis. And again, the telescope is a CDK 24-inch telescope, and it was installed in Charlestown. This was at the end of 2014 into 15 and became operational at the beginning of 2016. We do have a small refractor on top with a camera. You're looking at the back end of the telescope, very NP 127 5-inch refractor. The cameras that we have installed on the telescope, on the main telescope, is an SBIG 16803 research grade camera. And on the smaller 5-inch refracting telescope is an SBIG 8300 with filter wheels. So let's take a look. And I just wanted to give you a preview of the screen that you'll see when Dr. Miller and her students take over with a star party. There's a lot on here. Over on the upper left-hand side, we have the telescope STI control software. And down below there is our software for controlling the dome and the shutter mechanism to open up. And here you have a live view of the telescope inside of the 32-foot dome. It's actually pretty impressive to see, even remotely. And our images will appear over here on this screen here. And this is the camera control. We're going to be using the camera at the bottom of the telescope to acquire images of the sky. One thing I'm showing here is another new piece of software that we have just this year. A very exciting project for our faculty and our students is we've joined the world's largest robotic telescope network called Skynet, and it's operated and administered by a partnership with the University of North Carolina through a $3.5 million NSF grant. And what this allows us to do, it allows easy access, student access to the telescope, access to a number of labs, and also, most importantly, not only can we use our telescope, but we can use telescopes around the globe, from Cerro Tololo, Chile, to telescopes in Canada, Australia, and even in Europe. All right, so this is just a brief overview of the Skynet Robotic Telescope Network. And again, there are 2 NSF-funded Skynet labs. The first one is Our Place in Space, and we are currently integrating that into several of our courses into the curriculum, where students, both undergrad and graduate students, can utilize not only the APUS telescope, but also these telescopes I mentioned around the globe. There are about 15 telescopes that we have access to. And our telescope is one of the larger ones. It's not the largest. There's one that is slightly larger, but we do have a large 24-inch Cassegrain reflecting telescope. The other lab is a brand new lab, NS-funded lab, that's called the Multi-Wavelength Universe. And this will be utilized primarily in upper level courses, undergraduate courses, and as well as in for student research projects. We also have access to, as part of that Multi-Wavelength Universe lab, access to a 40-foot telescope at Green Bank Radio Observatory, also located in West Virginia. So it's pretty cool. So we get to look at the universe in various optical wavelengths as well as radio wavelengths. Okay, and just some of the advantages for our students is that this gives us a enhanced student engagement and really a hands-on experience with these telescopes. As I've already mentioned, there's a global robotic telescope access. We have access to telescopes worldwide. The interactive remote observatory allows for, doesn't really matter where you are, hands-on ease telescope operation utilizing the Skynet software. And also students acquire practical skills in handling data. Many of our graduate students are acquiring observations of planets around other stars and variable stars, and they can work with that data acquired from not only our telescope, but these telescopes elsewhere. So students will theory and practice by integrating the Skynet into the curriculum and to various research projects. So with that, and I promised Kristen I would try to keep that down below 10 minutes, and I think I'm at the 10-minute mark. So I am going to hand it off, and you can see Dr. Miller and our wonderful students here who are going to take us on a tour of the cosmos with our star party. So it's all yours, Kristen.
Thank you so much, Ed, and thank you for all your support and leadership for our program. Hello, everyone. We're really excited to be here with you tonight. I'm really hopeful that the sky will cooperate, fingers crossed. But we are the APUS Space Studies Research Program, and we are comprised of students who are working on both the Supernova Search Program here at APUS, as well as the Exoplanet Transit Program. And the students tonight are going to take you on a little tour of these objects. So first, let me share my screen. We're going to go live to our telescope. So here we are. You can see our telescope here in the center, and I thought it might be kind of fun. Actually, I'm gonna turn it just slightly. Let's slew it over just a little bit more. Let's put it on this one. And we are going to, you'll see it moves. We can control it remotely. We're gonna move it over and I'm gonna let you watch as we open it up today. But I want to get it this to move my Zoom bar. There we go. We're gonna let you guys kind of watch as we open some parts of the telescope because it's kind of fun to watch that. So this is a side view of the telescope, and you can see the dome moving. The dome and the telescope are coordinated, so they move together. And what we're going to do, the telescope itself has a cover over the mirror that protects it from dust. And we're going to go ahead and open that for observing. And you're going to see here on the side, you'll start to see these little pieces, these little flaps that come up and open on each side. The other two sides are going to open up. I always think that's kind of cool. Here comes one right here. And it opens up and lets us know that our telescope is ready for use. The other thing I'm going to do is I'm going to open our dome now that our dome has stopped moving and it's ready to get started. The dome's a little bit slower. It takes it a while to get going. There's a heavy piece. It's moving. There we go. But it will, the dome opens here and you can start to see the night sky through it, which is kind of cool. While that is opening, I'm going to move this over just slightly on the screen. And while it opens, I'm going to go ahead and get things set up for our observing here and move these programs into place so that we are ready to get started with our scripting runs. Here we go. All right. And I'm also going to position the telescope. I'm going to reposition it back to a better position to start the script in while the dome is opening, and then we'll be ready to get going. Okay, there we go. All right. We're looking back. The dome is now in what we call the home position. Sorry, the telescope's in the home position. The dome is moving to join it, and you can see that the dome is pretty much open at this point. There we go.
We should also
And we are
mention
open.
that although it looks like we left the lights on in the observatory, it's pitch dark in the observatory. We have an infrared camera that's shining infrared light in there so that you can see what's going on. But if you were in the dome right now, it would be hard to even see your hand in front of your face. It's very, very dark in there when we do observation.
That's so important for observing. We don't need any light, especially on a partly cloudy night. We want the perfect conditions in the dome to help us. Thanks for adding that. I appreciate that. All right, we're ready to get started with our observations tonight. And our first object is going to be introduced by James Berg. So James, I will let you take it away.
Hey, how's it going? Hello, everybody. Welcome to the Star Party. My name is James Berg. I'm an undergrad student for space studies with a major in astronomy at AMU, as well as a member of the supernova research team. The first object we're going to look at tonight is the Hercules globular cluster, which was first discovered in 1714 by Edmund Halley. He described it as a little patch in a constellation Hercules, something you could barely see with the naked eye on a really dark night. In 1764, Charles Messier added it to his catalog as Messier 13. The Hercules cluster is one of the biggest and most famous, one of the most brightest and most famous globular clusters in the Northern Hemisphere. It's about 25,000 light years away. It's easy to find with binoculars or a small telescope. It appears like a hazy ball to the naked eye under dark skies between May and September. If you zoom in closer to it, you can start to distinguish between the stars, which is why it's so popular to amateur astronomers. We should be able to see some detail tonight, even though we're only taking about a minute of exposure. It's about 145 light years in diameter, contains between 300,000 to 500,000 stars. The core density is extreme. Stars are only a fraction of a light year apart. Putting that into perspective, the cluster is packed 500 times closer together than what we see around our own sun, while our nearest star is about 4.2 light years away. The stars in this cluster are 11 to 12 billion years old, almost as old as the Milky Way galaxy, which is 13.6 billion years old. A lot of the stars in the Hercules cluster are smaller than our sun, which is why they've lived for so long. The bigger stars burnt out long ago, which we're looking at today, are the descendants of those stars later in their life cycles. Some of them have become red giants, expanding much larger and glowing with a reddish-orange light, much cooler than on the surface, but bright because of their size. The cluster has many of these red giants and some blue stragglers. Globular clusters like M13 help us study stellar evolution because all stars formed roughly around the same time, but they have different masses. They give us clues about the early Milky Way and conditions under which the galaxies form. In 1974, M13 was targeted with the Arecibo radio message, which was our first attempt at contacting potential extraterrestrial civilizations. It was sent to this cluster because we believed that it was a higher chance to reach life since that's a compact area. The message contained the numbers 1 through 10 in binary, basic atomic numbers like hydrogen, carbon, nitrogen, oxygen, and phosphorus, which are the elements of life, a sketch of DNA, the double helix, a stick figure with the average height of a human, the population of Earth at the time, the diagram of our solar system with Earth highlighted, and a drawing of the Arecibo telescope, which is located in Puerto Rico. And what you're seeing now is the globular cluster about 25,000 light years away from Earth. So take a moment to take a look at it.
Thank you so much, James. That was awesome. And we got, in spite of the cloudiness that you can see in here, this is a really beautiful image. You can see so many stars in here. I personally love globular clusters. I think they're just so beautiful because they're so densely packed, and it's just really, really pretty to see that starlight. So pretty exciting. And yeah, not a bad image considering there's some clouds out tonight. So we'll take it. James, you did a great job of describing to us, what this cluster is and where you can find it. It's one of the brighter ones in our night sky. I think it's really beautiful. And you could even zoom in a little more if we wanted to here. Yeah, the zoom controls are really getting in my way here. Here we go. There we go. Yeah, you can really look in and see the detail there. It's really pretty impressive. All right, I can see the telescope is moving to our next image, so I'm going to turn it over to Melanie Krausen.
Flu ended.
Hello, I'm Melanie. I'm an adjunct professor in space studies and astronomy here at APUS. I was the director of education and astronomy at the Astronomical Research Institute in North Carolina for about 4 years. And I helped to start the supernova research project here at APU when I was a undergrad and then a graduate student. And so now I get to be here. I really love APUS. It's great school, great environment, great students, great colleagues, great professors. And the courses we offer are pretty awesome too. The object I chose was planetary nebula. It has nothing to do with planets, but it's left over from the collapse of a sun-like star. These type of nebulae tend to be more circular and a little more compact than supernova nebulas that are left behind. This one is called the Dumbbell Nebula, also known as M27. It's in the constellation Vulpecula. It's a very faint constellation, just two tiny, very faint stars, two little stars, but it's supposed to make up a fox. It's just one little star hop in between the constellations Cygnus the Swan and Sagitta the Arrow. It's best seen under dark skies where you can tease out some more details with a telescope, or if you're brave enough to venture with binoculars and attempt to find it that way. It's very faint. It's deceptively faint. Um, it's at a magnitude of 7.4, so that's relatively bright. It's just below what you can see with the unaided eye, but it's still pretty bright as far as a telescopic object goes. Um, but because it's in a nice little dark area of space without too many bright guide stars getting you there, it can be deceptively tricky to find sometimes. Um, but it's best seen from in the summertime when it's high overhead, and it's in the midst of the Milky Way band. In reality, this nebula is about 13 to 1400 light years away. So you've got anywhere from late spring through mid-fall to really take a look at it, and highest overhead in the summertime. The width of the nebula is about 1.5, 1.4, 1.45 light years across. So it's a pretty interesting little object. It's called the Dumbbell Nebula. I always thought it looked like an eaten apple core. It's more what it looks like to be, but it's very neat. Um, yeah, I chose this one because I really like it. It's very fun, very rewarding when you get the chance to spot it in a telescope. I just saw it and found it in a telescope last weekend, so it was really neat. And this one's pretty cool because this was discovered by Charles Messier in July of 1764 from Paris. It was the same year he became a member of the Royal Astronomical Society. And when he started compiling his now famous Messier catalog of different objects, of 109, 110 objects that are not comets. And so that's what he was making the catalog for. So it's a really neat object, very fun to look at, very important for telling us about how stars and sun-like stars evolve and end their lives. I believe that's my time.
Nice. Thank you so much, Melanie. That image is coming right out here in just a minute, but that was a really great introduction to the Dumbbell Nebula. Planetary nebulae are really interesting. And I was thinking, as you said, it's a light year across. Just for reference, the Earth is about 8 light minutes from the sun. So you think about a light minute compared to a light year, and that just, the Earth's sun distance, and multiply that out in your head, and it's just, I mean, this is an enormous object. It's not going to look that big on our image. It's going to be kind of small because it was so far away, but it's mind-boggling to think about the distances in space. I'm so glad that you mentioned that. That's interesting. Pretty cool. How did your image of it turn out?
Trillion. Let's see. Sure. That makes this
Nice.
object about 9 light years across, or 9 trillion miles. Sorry, 9 trillion miles. Yeah, light year, 1.5 light years,
Wow.
9 trillion miles.
Wow. I mean,
Yeah, I think
that's,
this one's
that's
gonna be
hard to
really good.
even
I'm
imagine it, right?
monitoring
And
the
there we
Right?
are.
Too
Look
many
at that.
look at that. Yeah, there's a real clear
Fabulous.
patch of sky moving overhead now. I'm
We
watching
got
this.
super
Yeah,
lucky. It happened to be
beautiful.
in the right part of the sky.
Yeah, that turned out awesome.
All of this nebulosity is, part of the image. And it's really interesting that they are circular objects, but, the line of sight can, as you add up that dust, it can give us this structural element. I like your analogy of an apple core. I can really see that in there. All right, let's zoom into it a little bit more because that's always fun. Get a really close-up view in here. You can really start to see some of the interior structure in here, some of these lanes and some of the edges of that nebula. Zoom back out. All right, and I see that our telescope is moving again, which means it's time for our next object, which is Stephan's quintet. And appropriately, Steve Sims is going to tell us about it. So Steve, I'll let you take it away.
Well, thank you. Hello, my name is Steve, and I'm a student at APU pursuing a master's degree in space studies with an emphasis in astronomy. I was introduced to the exoplanet group last year as part of one of my courses, and since I'm interested in exoplanet research, I asked to join the group. The object I've chosen this evening is a group of galaxies that astronomers refer to as Stephan's Quintet. Now, a galaxy is a vast system of stars, gas. Stephan's Quintet is a compact group of 5 galaxies located in the constellation Pegasus. It was first discovered by the French astronomer Edward Stephan, which is how it's got its name. Stephan's Quintet is about 290 million light years from Earth. The term light year can be a little confusing. A light year is not a measure of time, but a measure of distance. The light year refers to the distance light can travel in 1 year. Now, Stephan's Quintet has 5 members, is one of the more visually striking galaxies. It's somewhat odd and distorted. It just doesn't look like your typical galaxy with spiral arms and lanes of dust. Stephan's Quintet is what astronomers refer to as a galaxy cluster. A galaxy cluster is a group of galaxies bound together by their gravity, making it a visually striking object to observe. What makes this cluster interesting is that 4 of the galaxies are physically close together and actively interacting with each other. At the same time, one of them, the large galaxy to the side of the other 4 galaxies, is actually much closer, happens to appear in the same line of sight. Still, it isn't considered a member of the galaxy cluster. So that galaxy is essentially photobombing in the picture. So this cluster really doesn't have 5 members, but only 4. However, the term Stephan's Quintet is stuck. The 4 interacting galaxies to the right that appear on the one after another are engaged in a cosmic collision. Their mutual gravity pulls on each other, distorting their shapes, which is why each galaxy seems so unusual, exhibiting misshapen tails of stars and gas, triggering bursts of new star formation. This is why the 4 galaxies appear misshapen and strange, so they are pulling on each other. So why is this important? Why do astronomers study colliding galaxies? It's not only a visual striking object to observe, but also a natural laboratory for studying galaxy collisions and star formation. It provides astronomers with a close-up view of how galaxies merge and evolve, a process to believe common occurrence in the universe. In summary, Stephan's Quintet is not just a pretty picture, but a cosmic laboratory. By studying it, astronomers gain insight into galaxy collisions and star formation.
Oh, nice job, Steve. Thank you so much. That's such interesting information, and it's really fun to have a galaxy cluster in here. It's these galaxies you can see they're different from the stars in the object because they have that little bit of extended nebulosity around them, and that's what helps you identify the galaxies in this little cluster. I'm so glad that you told us about it. It's really, really interesting. And interesting that they're not really all part of the cluster, right? Astronomy has a lot of things that we keep those names even though they aren't completely true anymore. Well, it's time to move on to our next object, and Kirsten Denhoff will tell us about that one. So, Kirsten,
Of
I'll let you take it
course.
away.
Can everyone hear me?
Mhm.
We're good? Awesome.
Perfect.
All right. Good evening, ladies and gentlemen, boys and girls of all ages. Welcome to the Star Party. My name is Keston Denalter. I'm a graduate student here at APUS, pursuing a Master's of Space Studies with a concentration in astronomy. I'm also a researcher with the Supernova Research Group and an analog astronaut with the APUS Analog Research Group. Tonight, I'll be sharing the story of the Veil Nebula. While it's not easily visible tonight due to seasonal timing and atmospheric conditions, we'll use a little imagination to explore its beauty together. So without further ado, let's get this party started. The center of the Veil Nebula is located approximately 2,600 light years away from Earth and is composed of 3 main parts: the Eastern Veil, the Western Veil, and Pickering's Triangle. The entire Cygnus loop, including all 3 parts, spans a total of 120 light years across. It can be observed towards the end of the summer season, specifically in September, around 11 p.m., crossing the meridian. When viewed in the night sky, it has an apparent magnitude of 7.0. While we cannot see it in its entirety tonight, the full size of the nebula on a clear, dark night has a width of 6 full moons. I know, shocking. The Veil Nebula, also known as the Cygnus Loop, or NGC 6992, is a cloud of heated and ionized gas and dust that lines the visible portions of a supernova remnant. Supernova remnants are the expanding structures formed after a star explodes in a supernova, either through core collapse or thermonuclear runaway. The explosion ejects stellar material at extremely high velocities, sweeping up surrounding interstellar gas and material in a powerful shockwave. This interaction produces a glowing shell of ionized gas, with emissions at various wavelengths, revealing the presence of elements such as oxygen, sulfur, helium, and hydrogen. These remnants evolve over thousands of years, shaping galactic morphology and seeding space with these heavy elements. The Veil Nebula was thought to have begun between 5 and 10,000 years ago, from the remnants of a supernova explosion of a star believed to have been 20 times the mass of our sun. This supernova explosion would have been brighter than Venus in the night sky when it occurred. William Herschel first discovered the nebula on the night of September 5th, 1784. Its complex structure and varying brightness throughout the nebula have made it a favorite object among astronomers to study supernova remnants and nebulae morphology. So let's try a quick exercise in imagination. We can kind of see, I want you to either close your eyes just to imagine it, or squint if you can, to try and make out the image. Okay, ready? Now I want you to imagine a campfire, and you are sitting beside it, gazing up, watching the smoke drift off into the sky. You see this array of twisting, curling, long ribbons of gray or white smoke. That is precisely what the Veil Nebula looks like, only far, far larger and infinitely more beautiful. You can open your eyes, by the way, now if you want to. While not a solid object, its cosmic luminescence showcases a brilliant design of threads, like a beautiful tapestry woven in the stars. Its colors are a mix of bright blues and greens, representing the oxygen elements within. It also contains warmer undertones of reds and pinks, elements of hydrogen and sulfur forged from a star that shines no more. Even today, the Veil Nebula continues to shine brilliantly. Its glowing gas is a lingering echo of the supernova that tore through space thousands of years ago. As it gradually cools and fades over the next 100,000 years, we remain incredibly fortunate to witness this breathtaking cosmic masterpiece. So tonight, even if we cannot see it with our own eyes entirely, very vaguely here, I hope you're able to see it with your imagination as well. Though the star that birthed it is long gone, the Veil Nebula continues to whisper its story across the night sky for us to observe. Thank you, and I hope you enjoy the rest of the Star Party.
Thank you so much, Keston. That was fantastic. And we really didn't think we'd be able to see it at all with the sky conditions tonight, but you can actually I'm seeing those strands and that structure in here. So it's kind of exciting that we're able to actually see a little bit of it. This is actually a pretty amazing picture of it.
I'm amazed we can actually see some of the ripples there, the curtains I was talking about with the smoke. It's impressive.
Yeah. All right, we're moving to our next object, and it is going to be, we're going to turn the time over to Nick Foley to tell us about it.
Hey everyone, my name is Nicholas Foley, a recent graduate of American Military University and a member of both supernovae and exoplanet research teams. A month ago, I successfully achieved a Bachelor's of Science in Space Studies with an astronomy concentration. Before my academic journey, I was an unmanned aerial systems operator in the U.S. Army, and it is fun applying my military experience around drone technology to astronomical research. What lies next for me is my master's program in space systems at Embry-Riddle Aeronautical University. I hope to gain a career in space exploration, especially in exoplanet research. I've always been fascinated by space, the stars, the planets, and witnessing humanity reach for them. Speaking of space exploration, let's take a few minutes to journey together to one of the most remarkable sights in the night sky, the Andromeda Galaxy. The Andromeda Galaxy, also known as Messier 31, is the nearest major galaxy to our own Milky Way. Even with the naked eye, on dark nights far from city lights, you can spot it as a faint, fuzzy patch in the constellation Andromeda. What you're actually seeing, though, is a system of 1 trillion stars, each possibly hosting planets like ours. Andromeda is about 2.5 million light years away. That means the light entering your eye tonight left Andromeda when early humans were just beginning to use stone tools on Earth. In other words, when we look at Andromeda, we are looking back in time. Astronomers also know that Andromeda and the Milky Way are on a collision course, but don't worry, it won't happen for another 4 billion years. But when it does, the two galaxies will merge into a giant elliptical galaxy, sometimes nicknamed Andromeda. While that sounds dramatic, keep in mind that stars are so far apart that very few will actually collide. Instead, the galaxies will weave together into a slow cosmic dance, reshaping the night sky for whatever beings are around to see it. Andromeda also played a crucial role in changing how we understand the universe. For centuries, astronomers debated whether the Milky Way contained everything there was, or whether those faint spiral nebulae in the sky were actually entire galaxies of their own. In the 1920s, astronomer Edwin Hubble used the newly built 100-inch telescope at Mount Wilson to measure the distance between stars in Andromeda. He proved that Andromeda lay far beyond the Milky Way. This discovery showed that our galaxy is just one of countless others, and it completely transformed our view of the universe from a single island to a vast cosmic ocean. Thank you.
Perfect timing, Nick. And here's is the picture. Look at this. This is an object which is easy to see in the night sky because it's very, very bright. And in fact, I'm going to zoom out a little bit. There we go. Because it's so big and bright that it fills so much of that image. But you can see the beautiful center of this galaxy, which is so bright. It's all the stars there. And then all of this this gorgeous nebulosity around it. And some of even you can even see some structure here with some dust lanes and other features in the image. So it's a beautiful image and a really great job explaining it. Thank you so much. It's really, really pretty. This is kind of a very striking image. You can, as everyone can see, our night has actually, knock on wood, gotten progressively better as the night went on. We've got the beautiful dark background and of the night sky and the brilliant white of the stars. This is the kind of image that astronomers love. So I'm pretty excited about it. I'm going to go ahead. I think we have 1 minute that I have time to zoom in again so you can see some of that really pretty structure on there.
It's a very good image indeed. You can definitely, what you're seeing is just the core of it too. There's definitely arms, like just like the Milky Way or the other spiral galaxies you'll see. But with this image, yeah, we're just seeing the 1 minute exposure. We're just seeing most of the core, and then yeah, there's still more to it. It's very big, actually.
It is. It's an enormous galaxy, and you can see some faint hints of some of those dust lanes that make up that spiral structure in here, which is kind of cool to see. But yes, the center is so bright, it's exposing out a lot of the image. So wonderful. Well, thank you for telling us about it. This is a great and exciting image. All right, our next object, Jason Couchard is going to tell us about it. So Jason, I'll let you go ahead.
Thank you, Dr. Miller. Greetings, everyone. First and foremost, I just want to say thank you for everyone here for attending tonight's event. My name is Jason Couchard, and I've been a research student at American Public University for well over 6 years. Currently, I serve as the primary investigator for the Exoplanet Research Program and have worked with professors like Dr. Miller and Dr. Elbein throughout my time here at APUS. Now let's discuss the object we are slewing to, which is Messier 101, or the Pinwheel Galaxy. This galaxy was first discovered by Pierre Méchain in 1781 and was later confirmed by Charles Messier. The Pinwheel Galaxy is a spiral galaxy located 21 million light years away in the constellation of Ursa Major. The diameter of this galaxy is around 170,000 light years, which is almost twice as long as the diameter of the Milky Way galaxy. Throughout the arms, you'll notice several bright spots, which are actually stellar nurseries or star-forming nebula. Once the image is finished processing, you'll be able to notice these bright spots throughout the arms of the Pinwheel Galaxy. In the image, though, you'll notice one specific nebula called NGC 5462, which is located in the middle of the left side of the image. That bright region, as you might not think too much about it outright, is a star-forming nebula. And this nebula contains many, many blue giant stars. This region is also known to produce several supernova throughout the years, which is an area of interest to our research programs. And this is just one of the many nebula within the Pinwheel Galaxy. There is about 11 in total that have their own NGC designation codes. There are many more that don't have an NGC designation code. That is all for the Pinwheel Galaxy. Thank you again. And Dr. Miller, you know, when you're ready.
It's taking the image right now, so we should be able to see that soon. It's pretty exciting, isn't it, that we can find and image star forming regions in other galaxies. And Jason, correct me if I'm wrong, but I think our group has actually looked at a supernova in this galaxy. I want to say a couple of years ago. Am I remembering that right?
Yes, I believe it was about three years ago. We looked at one, and that was a very, very exciting time for the research program.
Mm-hmm. Supernovae actually occur, actually really frequently, but they're such random events that you have to kind of be watching for them. And so they're, we miss a lot of them. And this was one that had been observed. Another group had discovered it, and we were able to look at it just a short time afterwards. And so it was pretty exciting to be able to see that and to compare it with our images and see, oh dear, I think our luck may have just run out. Shoot, it should be right about there. Oh, we've gotten so lucky tonight with our beautiful images and just happening to hit the parts of the sky that do not have any clouds in them. And yeah, it should be almost exactly right here on our image, which means that we are looking through clouds there. This is not the kind of image that astronomers like to see, but they unfortunately happen frequently. So I'm so sorry for that. If we have time at the end, we can pull up one of our images of this galaxy and show it to you. But yeah, we'll hope those clouds move out of our way and that's not not going to color the rest of the observing, because we've gotten so lucky with some of these images. Hopefully that will move out of our way. But thank you so much, Jason. That was really great and lots of really good information. We appreciate it.
Of course.
All right, our next image, fingers crossed, it's not in a cloud. Our next image, Selena Pena is going to tell us about it. So Selena, we'll let you go ahead.
Good evening, everyone, and welcome to tonight's stargazing. Well, hopefully. So my name is Selena Pena. I am a graduate of APUS with a master's degree in space studies, and my focus is on astronomy. I joined the supernova research team back in December of 2020. I joined because driven by a desire for hands-on experience with real astronomical data and the opportunity to contribute to a project that, bridges that learning with discovery. So especially about our cosmos. I've had the pleasure of using Wally on my last ILMA mission back in May, observing Had's variable star. So as the telescope slews and snaps pictures, I'm going to talk to you a little bit about the Bubble Nebula, also known as NGC 7635. The Bubble Nebula was actually discovered in 1787 by William Herschel, one of the great early catalogers of the deep sky objects, if you're not familiar with them. The nebula is located in the constellation Cassiopeia, and when you recognize it, you're gonna find it in a W shape in the night sky, so it's pretty cool. It's best seen in the northern hemisphere, usually September through February. It's about 7,000 to 11,000 light years away from Earth. The bubble itself is about 7 light years across. So the bubble nebula actually gets its name because it looks like a giant soap bubble in space. And then it's created by stellar winds from a massive hot star that lurks inside of it. So It's pretty cool. Because it does have an apparent magnitude of about 10, it is too faint to see with the naked eye. So as you can see here, you need this awesome telescope to observe that. The importance of it, I think it's huge. It does have a dramatic effect that massive stars have on their environments. The hot O-type star at the center is about, actually it's approximately 45 times the mass of our sun, and its stellar wind, again, that's what sculpts the bubble shape that you see there. The reason I chose this nebula is because, actually a couple reasons. It reminds me of my daughter's love for bubbles, and she likes to torture her dog with it. He always eats them. That's my reason. And it's one of the most visually striking examples of how powerful and energetic stars can shape their surroundings. So I just find it quite fascinating.
Thank you so much, Selena.
Thank you.
It's
Yeah.
really, oh, I'm so sorry. Go ahead.
No, I was just saying thank you.
Yeah, it is really interesting, isn't it? How stars can just, just shape a huge, enormous region around them. And it looks like you got lucky and this was a better position in the sky. So I'm really glad for that. Thank you so much. Our
Thank
next
you.
object, Melissa West is going to tell us about it. So Melissa, I'll let you go ahead.
Thanks, Dr. Miller. Good evening, everyone. My name is Melissa, and I graduated from AMU 2 years ago with a bachelor's degree in space studies, concentrating in astronomy. I joined the supernova group about 4 years ago, focusing on identifying supernovae, and I love working with our telescopic images and hoping to find something new. I'm passionate about making the cosmos more accessible to the general public, and so I'm currently pursuing courses in data visualization to help reach this goal. I am also the website coordinator for this group. Our website tells you what projects we're involved with, some of our telescopic detections, and articles written by members of our group. And that link should be in the description below, so go check it out. Tonight, I'll be talking about the Lost in Space galaxy. So the Lost in Space galaxy is a spiral galaxy, which means that it has spiral arms surrounding a central core, like our Milky Way. And it was discovered by a German astronomer, Arthur von Auwers, in 1854. It's located about 18 million light years away within the constellation Draco the Dragon. The cool thing about this object is that it's considered as a circumpolar object, meaning that throughout the year, it goes around the North Star Polaris, so it never dips below the horizon. This galaxy is about 1/3 the size of our Milky Way, so it's technically a dwarf galaxy. There's a reason why this galaxy is called Lost in Space. Most galaxies come together as groups, and then these groups form clusters, and these clusters form superclusters. Our Milky Way is part of the local group alongside the Andromeda galaxy, which we saw earlier, and about 90 other galaxies. Our group is part of the Virgo cluster, which is part of the larger Virgo supercluster, and that's a part of a much, much larger Linnaeus supercluster. Imagine, if you will, these large structures forming a cosmic web, where you have filaments of superclusters leaving areas of emptiness in between. The Lost in Space galaxy is found on the edge of one of these empty patches called the local void, and it stretches out about 150 million years. And it looks lonely because there's nothing close to it, hence the name. Just to offer some perspective, the Andromeda galaxy is only, as a relative term, 2.5 million light years away. And there it is. I personally would love to learn more about how this galaxy ended up so far away and isolated from others. Maybe the universe's expansion isn't as uniformly distributed as we thought. Who knows? And as you can see here, how it's kind of edge on and still a bright core that you could see also. So yeah, there you have it. I hope you enjoyed learning a bit about the Lost in Space galaxy. Since the theme of this conference is to honor the Hubble Space Telescope, I urge you to look up Hubble's picture of this galaxy and any other object that we've talked about tonight. Thanks for listening.
Yeah, I love that you mentioned the Hubble telescope because those pictures are really, really gorgeous. And of course, ours tonight are just a very quick, 1 minute look at each one. But when you have a space telescope devoting time to it, they're stunning images. So I second that. Go and look these up because you'll be amazed. And this image is really quite pretty. You can see that you just got that bright core you were talking about, and even you can kind of see it's edge on, so it's hard to tell, but you can see some of the darker regions, which are the dust lanes that are outlining some of the bright spiral arms within this, just like our Milky Way has. So it's kind of cool. And then, it goes to this more diffuse material around it. Very traditional spiral look to it. It's a really interesting galaxy. I think it's kind of funny that we thought it was lonely. I don't think it's lonely, but but it is certainly out there, and it's interesting to think about how that happened. Right? So many things that we don't yet understand in our universe. And that's part of what makes astronomy a really exciting field to study. There's still a lot of answers that we're chasing and that we'll find. Melissa, that was wonderful. Thank you so much. Our next image will be narrated by Ryan. So Ryan, I'll let you go ahead and tell us about your object.
Thank you, Dr. Miller. Good evening, everyone. Thank you all for being here tonight and taking part in our STAR party. My name is Ryan Nadolski, and I serve as the training coordinator for the Supernovae Search Group. And outside of astronomy, I'm a student here at APUS and a father of 3. So my hands are full. But tonight I would like to talk to you about one of the most iconic nebulae in the night sky, and that's the Ring Nebula. The Ring Nebula is also known as Messier 57, is a planetary nebula located in the constellation of Lyra. It lies approximately 2,500 light years away from Earth, and through a small telescope, it appears as a delicate smoke ring suspended in space, which is how it earned its famous name. And to understand the Ring Nebula, it's helpful to know what a planetary nebula is. And it is a misleading name. Planetary nebulae have nothing to do with planets. They form when a star, like our sun, runs out of its fuel. As the star ages, it sheds its outer layers into space, leaving behind that glowing cloud of ionized gas. And at its core remains that white dwarf. So when the image shows, if we get lucky and there's no clouds, you should be able to see it in the image. And the Ring Nebula, it's a textbook example of this process. And like I said, at its center lies that white dwarf. And that white dwarf has a surface temperature of more than 100,000 degrees Kelvin, so it's very hot. And it's no larger than Earth. It contains about half the mass of the sun, though. So that means that a single teaspoon of its matter would weigh tons. So illustrating just how extreme and dense white dwarfs really are. The surrounding ring that we see is actually a 3-dimensional shell of gas. So it's more of a donut and not a flat circle. When its appearance, with its appearance shaped by our line of sight. One of the most fascinating aspects of the Ring Nebula is that structure. And recent images from the James Webb Space Telescope revealed intricate details, including small clumps of gas that look like tiny comets. Multiple shells created by past outbursts, and a faint outer halo stretching far beyond that bright ring. These features highlight the turbulent, complex process of the star's final stages. Studying the Ring Nebula provides valuable insights into the life cycles of stars and how they enrich the galaxy. So the expulsion of carbon, nitrogen, and oxygen is essential for forming those new stars, planets, and eventually life itself. In this way, the Ring Nebula is not just an end, but it's also a beginning, playing a role in the recycling of matter across the cosmos. So in summary, the Ring Nebula is both a breathtaking sight, as you can see by the image, And it's also a critical piece of the puzzle of stellar evolution. And so by observing it, we not only witness the beauty of a dying star, but we also gain a glimpse of the future that awaits our own sun billions of years from now. Not tomorrow, don't worry. Thank you for your attention. And again, thank you for joining our Star Party.
Thank you so much, Ryan. You can see that this is a much brighter nebula. It's closer and it's brighter than some of the other ones that we've looked at tonight. But you can still see some of that the darker area in between where we're not looking through as much of the nebula on the sides. It kind of adds up as you look through it and makes it brighter. And then in the middle, you're just looking through that one layer of it and gives you that dark appearance through it. So it really does have that ring-like appearance with that in there. It was a wonderful description of it, and we really appreciate you telling us about it. That is the end of our observing run. We hope that you have enjoyed looking at these objects. We got really lucky with most of them. We're ending here on a gorgeous gorgeous image and a really beautiful part of the sky. So I'm happy that we're ending on a good note. But we want to thank everybody for joining us. We want to thank you for thank all of the student presenters for doing a fantastic job in telling us about these unique and beautiful and really fascinating objects in our night sky. And thanks for coming to the SESA conference. We hope to see you tomorrow. We have some really interesting panels, including an observational astronomy panel tomorrow, where you can learn more about astronomy observations, and an analog research panel where you can learn more about some of the analog research groups that we've done. Please also come to the poster session at noon. Some of the students that you've heard from tonight will be presenting posters there as well about some of the research at APUS. So we hope that you'll be able to attend. Thank you, everyone. And we hope that you've enjoyed the Star Party. Thanks for being here.